Well, thank you very much again for allowing me to talk. So we've heard some very good presentations so far this morning about water and the scientific aspects of it. I'm going to talk a little bit more about water from the resource perspective. So yesterday you heard me hopefully talk a little bit about ISRU, in situ resource utilization, mostly about the moon, as well as the dual paths. So now stepping back a little bit more, some of these charts I created a number of years ago, so you don't see the icy moons on here, you don't see Mercury, which probably should be added, especially when we talk about water. But this chart is mostly related to what we might do from a human mission perspective. So I have the moon, Mars, and asteroids, which is what NASA has been looking at through most of my career. There are four major resources that we consider as being essential for longer-term sustained applications, water being the biggest one. You can find it at each of these different locations, and I'll go into that a little bit more. It has tremendous usages, which I'll mention, but we also, again, as I mentioned yesterday, we're interested in the oxygen. Definitely carbon sources. So we heard a little bit about the organics on asteroids or on the comets, but a carbon source is very important, and then the metals, as I mentioned before. So from a NASA perspective, especially from the lunar perspective, we look at water as basically game-changing. If you have it, you have water, which is drinking, radiation shielding, plant growth. It also is a fantastic source of hydrogen, which is also and oxygen, which are important for rocket fuels, fuel cell reactants, and such. Hydrogen, again, as you'll see in the next chart, is very important from a processing perspective. It is, as we've kind of heard a little bit about, when you talk about water, you actually have to start going to potentially very specific locations, and there are implications for going to those very specific locations that you have to take into consideration. Oxygen on the moon, metals, much more ubiquitous, in particular with the moon. 40% or more by mass of the minerals on the moon is oxygen, so you can find it almost anywhere in different forms of metals. And when we think about rocket propulsion, chemical in particular, typically oxygen makes up somewhere between 70 to 80% of the propellant mass. So just making oxygen alone is of tremendous interest through either directly from water or from these minerals. And then, as I mentioned the other day, we are interested in the manufacturing feedstocks and the construction feedstocks, and eventually getting to supporting life support, nutrients, food production, plastics. That's where the carbon source really comes into play. So this is an interesting chart. You kind of walk through, decision trees. You think about your resource type, you think about what you're bringing from Earth, whether it's reagent-wise or otherwise, what type of processing techniques you might be doing, resources of interest, and such, eventually getting to your products. And if you think about Mars, for example, on the left-hand side, you can start with the Mars atmosphere, primarily carbon dioxide with a little bit of nitrogen and argon, and you follow down that pathway, you definitely can get to the oxygen on its own. We see this with the MOXIE experiment on the Perseverance rover. However, when you add water to the mixture, you can start seeing that the combination of a carbon source and a water source, when you get down towards the bottom, you not just have your oxygen, your fuels, but you can start getting into your secondary products. And then throwing in nitrogen, you can get ammonia and other things of interest downstream. So having these understanding of the resource types and the implications for your processing and products is very important downstream. For the moon, again, talking a little bit, we've heard a little bit more about water on the moon. Really, it's still speculative. We have lots of very interesting orbital data. Spectroscopy was mentioned the other day. We have different ways of interpreting that data. One interpretation says that we may have water up to 30% weight in different permanently shadowed craters. The only real data source we have on the moon is L-Cross, and the plume suggests maybe 5.5 weight percent, but there's a plus or minus 3 weight percent variation on that. So it could be down, you know, in the 1% range and maybe in the 8% range. Still big question marks. With Mars, we know a lot more about it. We've heard some presentations about the radar spectrums and some of the missions. And I look at it that there's possibly 3 major water sources. There's the ubiquitous Mars soil that I'll talk about. There's hydrated minerals, which may contain larger amounts. And then there's the subsurface surface ice that you see starting at the poles and working southwards. Some of the big question marks are how far south does that ice sheet go? We have some very interesting data where craters have been formed, and you can literally see the ice in the new craters. So it gives you an idea of how deep that ice sheet might be and where it's located. An important aspect of looking for water and other resources is not just where it is or whether it's there, but you have to take into consideration a lot of the other factors. We just heard about energy. Is there an energy source nearby, whether it's sunlight or not? Is the terrain accessible? Is it in a location that I can get to that resource or not? Can I establish a base nearby? Can I establish communications with Earth or nearby aspects in the type of infrastructure? So to some extent, when you're thinking about water and other resources, you have to take all of those things into consideration. So L-Cross hit in a crater called Cabeus, extremely cold, very far from anywhere you would set up a base that you can actually mine this. So the water in Cabeus may or may not necessarily be considered a mineable resource because of those. So when we think about water as a resource and water as a mining, we basically see 3 major driving aspects. One is the method for how you're going to extract the water. And here's an example of something in a permanently shadowed crater. One is, how do you get the water out of the permanently shadowed crater? Because the humans are not going to be down there. Your customer is not going to be down there. So how are you going to get that water out of the crater? And then the big part, the third big part of that equation is, how do you get the energy into the permanently shadowed crater? Is it beamed? Is it a nuclear reactor down there? Do you have a long cable? All of those factor into how you're going to do these operations. And when you think about that first step, the mining, now you have to even go deeper. Well, where your mining technique will be based on the depth, the distribution of the water, how, as well as, you know, from a spatial perspective, is it homogeneous? Is it distributed? How hard it is? What are the geotechnical ideas? So here's just one example. We've looked at several where, you know, on the side there is Shackleton Crater, 20 kilometers in diameter. We're not going to mine that anytime soon. So we look at some of the smaller craters, ones that might have, are large enough that they would have potentially ice in there, but small enough that we can get in and out of them. And so we kind of notionally picked somewhere between 5 kilometers-ish for a travel distance. You see, if we set up a mine in this particular smaller permanently shadowed crater, we have a traverse path of approximately 2 kilograms to some kind of a site on the ridge where we think that there might be enough power, which would be within several kilometers of where we might set up a base. So these are the kind of things that you have to think about. I'm going to jump a little bit quicker before I talk about Mars, and this is a little bit more about the water on Mars and the pros and cons. We found from the SAM instrument on Curiosity that when you just pick up soil on the Mars surface, throw it in a crucible, heat it up, you actually find that there's somewhere between 1.5 and 3 weight% water there. I was just talking about the moon and mining water at 1 to 5 weight%. So here, ubiquitously on Mars surface, there's this granular material at 1 to 3 weight%. It's very mineable. We've done studies where we can actually put hardware on Mars, process that 1 to 3 weight% water, and actually, from a mass perspective, it saves you several tons of mass compared to bringing fuel from Earth. However, it is very low concentration. You require to heat it up to about 400 degrees centigrade. If you raise it higher than 400 degrees centigrade, you get more water, but you also now break down the perchlorates that are in the soil, and now you have hydrogen sulfide and some other things that you may not want to deal with. So you have this balancing act of how much water do I want versus what are the contaminants that might occur. We have gypsum and sulfates. These are veins that have potentially 10 to 20 weight% water, but now they're hard materials. I have to, basically excavate it and crush that material before I can process it. And then really interesting is that subsurface ice. How deep is it? There are, at the poles, it's on the surface. Phoenix lander landed there, blew off the dust. We saw ice literally there. Problem is when you send humans to Mars, there's a balancing act as to where you land. You can land the most at the equator. You get the most sunlight at the equator. If you go to the poles, less capabilities going there. So a lot of discussion has been going to those mid-latitude locations. So here again, how far north can you go for the ice? How far south can you go for having a worthwhile scientific mission and payload? So when we talk about early Mars situations, we will most likely have nuclear reactors. And now we have this balancing act of that first mission, do I go after the low weight% soil, where I would excavate and then bring that soil to some kind of central processing unit, typically on the same lander as our ascent vehicle, or do I actually start to mine water? And we have very interesting concepts called Rodriguez wells, where you can drill down, create a pool of water, and extract it. Over time, if we're there for longer periods, we'll want to do something greater. These are different techniques that we looked at for Mars, and interestingly enough, when I created these things, these charts like 5-6 years ago, when we were talking about Mars water processing, when we came back to doing lunar exploration, we realized most of these things are the same type of stuff. So we've worked on near water processes where you take a core down and down to a meter and heat it up. Honeybee Robotics has a very interesting technology called PVEX, or planetary volatile extractor, that we've worked on. We've talked about trying to take the material up to the surface through excavation or augers, depending on how hard that material is, putting that material into a reactor, heating it up, and driving off the water. So these are things that we have done a decade ago for Mars, and we're looking at for the moon. One of the really interesting ideas for the moon has been, can I beam energy down below the surface and just have the water vapor come up and we collect it? Turns out that's not as simple as it sounds, because different beaming techniques only heat certain parts of the subsurface, and what we've learned is if you don't have the right thermal profile, when you heat the water below the surface, it tends to go deeper or to the sides outside of where you just heated versus coming up to the surface. And then the one that I find very interesting, again, Honeybee Robotics has completed a recent technology work for NASA called Red Water. Again, look it up, where in Antarctica, to get water, you actually drill into the ice sheet and pump hot water down. It creates a pool of water, and you now can draw water out on a continuous basis, balancing that heat thermal energy in versus the water coming out. If I have a nuclear reactor on Mars, I have several tens of kilowatts of thermal energy that I can pump down, create this pool of water, and pull the water out fairly efficiently. So that's something that we are considering. An interesting point down at the bottom is a lot of people look at the pressure on Mars and they say, oh, well, we're close to the triple point of water. In actual fact, a colleague of mine pointed out that that's not really the case. When you look at triple points, you actually have to think of the partial pressure of water in that. So when we're on Mars, we are very much below the triple point of water, and so that's why it will be very hard to find water on Mars unless it's in a briny substance. And when we do these rod wells, we probably will have to have some kind of a pressurization cap to allow us to fill up that cavity to a higher pressure. An important point in all of this that we want to convey is before we do any of these resource extraction or mining techniques, we have to do a lot more science and a lot more measurements, starting with orbital measurements, doing some very early reconnaissance work, and as time goes on, more and more reconnaissance. We heard a little bit about that yesterday when we talked about going from, you know, a notional concept all the way to a proven reserve. And all at that time, you have to have what are called predictive models. What are the geotechnical contexts in which you're finding these data? So we propose that we work very closely with the science organizations. So it's not science or ISRU versus each other, it's exploration and science together. And when you look at the stream of the types of measurements that we need, yes, there are some very unique science measurements that occur. Yes, there are very unique ISRU or resource assessment measurements that we want. But the bulk of the data that we need to get will be in that central region. So one of the concerns that I've heard is, oh, well, we need, before you mine a permanently shadowed crater, we have to prove that there's, you know, understand the science there. By doing this, we will know more about that permanently shadowed crater than any science mission would ever have done. And so where we are with mining water on the moon or Mars is that it's all very predicated on mapping and doing these evaluations. And again, doing these responsibly, and how do you pick your locations? So these are things that are going on right now that we will continue to work on as time goes on. And I think this is my last chart, and this, again, my career has gone between looking at the moon, looking at Mars, back and forth, once considering going to an asteroid for a period of time. But through my 25-year slog of working in situ resource utilization, I've worked back and forth on these technologies, and I realized when you create a diagram that says, oh, if I'm only working on oxygen and metal extraction of regolith, here are the technologies I need. Oh, if I'm only working on extracting water from permanently shadowed craters or subsurface on Mars, here's what I need. Oh, if I want to just process the Mars atmosphere, here's what I need. You start seeing that the bulk of these technologies are really in the center there. So how do we do this logically? And then we ran some numbers, and I had a little bit to deal with this, but so on the moon, we were saying our initial production plant might be about 10 metric tons of oxygen over a year period of time. Early Mars missions, if you go to DRA 5.0 and other ones, we typically make somewhere between 20 and 30 metric tons for the crew to get off the Mars surface. But we have a longer period of time, 26 months. So when you look at the production amounts versus the time you have, you start seeing very similar processing rates. So now we could potentially not just have the same technologies, but we actually may have similar modules. And I just stack one or more modules depending on the processing rate I have. So this whole idea about using the moon as a stepping stone to Mars comes into play in many of these different factors. And with that, I'll bring my presentation to a close.